Okay, let's solve this problem. Do it quick, as quickly as possible. Okay, for this problem, I think I explained how to determine entropy generation. We can use entropy balance equation. So the entropy balance equation can be made by this equation: entropy transfer in minus entropy transfer out plus entropy generation, as gen is going to be the change of entropy of the system, which is the total entropy at the final state S2 minus the total entropy at the initial state S1. Then there are three entropy transfers that we can consider. The first one is by heat, which is Q over temperature. Q in over temperature. And there is no entropy transfer by work, because when work goes in and out, there is no change in entropy, because you do not create any waste form of energy when you transfer work. You only, create, the waste form of energy when heat is added or removed. So unless there is a heat transfer, there is no entropy change due to energy transfer by work. Then what about mass? Mass has thermal energy, so mass entering a system has entropy. So these two are entropy transfer in. What about entropy transfer out? We can consider that the same thing. Q out over temperature T plus mass leaving the system. This one has specific entropy. Plus entropy generation is going to be the change of entropy of a system. How do we determine that? Mass at the final state times specific entropy at the final state minus mass at the initial state times specific entropy at the initial state. So that is the entropy balance equation. To simplify that, we can consider a closed system. If you have a closed system, there is no mass entering or leaving the system. And we can combine Q and out. Say net heat transfer Q is Q in minus Q out. Then the energy balance equation, entropy balance equation, this one is going to be Q, the net heat transfer, over temperature T plus entropy generation is going to be the same as mass. Because it's a closed system, there is no change in mass. M2, the final mass, M1, the initial mass, should be the same. So mass times S2 minus S1. So this is entropy balance equation for a closed system. What about if we have an open system? Too fast? No? Okay. What about if we have an open system? Most open systems are steady state. So let's focus on steady state open system. Since it is a steady state, there is no final mass or initial mass. So we can neglect the right-hand side, and we can combine these two and say the same thing here, Q over T, but we have mass transfer in, mass transfer out, plus M in, S in, minus M out, S out, plus entropy generation is going to be 0. But when we talk about steady state open system in chapter 4, it was convenient to use the rate form. So why don't we say Q dot M dot N dot S dot. So this is the entropy balance equation for an open system. So we have two equations. That's it. So based on these two equations, let's solve this problem. We have an oxygen entering an insulated 12 centimeter diameter pipe. So we have a pipe. Pipe has an inlet and an exit. So it's an open system. So we can consider steady state open system. So let me write this equation here. Q dot over T plus M dot. By the way, it has only one entrance, one exit. So M dot at the inlet is the same as M dot at the exit. So I'm going to say M dot S in minus S out plus the rate of entropy generation is going to be 0. So this is our governing equation. It says it is an insulated pipe, so there is no heat transfer, so we can neglect the first term in this equation. So what can we do? We need to determine M dot. We need to determine S in minus S out. So let's do that. How can we determine M dot? There are two equations to determine M dot. M dot can be determined by either density times volumetric flow rate, or M dot can be determined by density times average velocity times cross-sectional area. So which one? We do not know the volumetric flow rate. So let's look at the other equation. Do we know the density? No, but we have a pressure, temperature. If you know pressure, temperature, can you determine the density? Yes. Our system is oxygen. When you have an oxygen, do you have any, the equation that we studied to evaluate their properties? Yes, ideal gas equation. So the ideal gas equation is PV is RT. Is there density? No, but we know the inverse of density is specific volume. So this ideal gas equation can be written as P over rho is RT. Okay. Then what is P? 240 kilopascal. What is T? 20 degrees Celsius. What is R? Is not given, but you can calculate R by universal gas constant R bar divided by molecular weight M. This M is not the mass of the system. This is the molecular weight of this oxygen. Where can you find this M? From table A1. Oxygen and molecular weight is 32 kilogram per kilomole. (32 kilogram per kilomole). What is the universal gas constant? You need to memorize them. Memorize it. 8.314 kilojoule per kilomole Kelvin. So we have everything. Can you determine the density? No, you can't, because you need to use Kelvin, not 20 degrees Celsius, 293 Kelvin. Then you get the density. When you get the density, this density goes here. What about the velocity? 70 meter per second, written here. 70 meter per second. What is the cross-sectional area? We do not know the cross-sectional area, but we know the diameter. If you know the diameter, you can determine the area. How? Pi d square over 5, 4, right? So d is 0.12 meter. So we have everything. Can you determine the mass? No, you can't. You can only determine the mass flow rate, not the mass. So if you do, the mass flow rate is 2.496. 2.496 kilogram per second. Don't forget the unit. Then the next one is S in minus S out. How can we determine S in minus S out? We studied entropy equation for pure gaseous system. If you don't remember, S2 minus S1 is Cp natural log T2 over T1 minus gas constant R natural log T2 over P1. Pretty sure that you remember this one, right? Then, oh, but this one is S in minus S out. Okay, can do that. S in minus S out. T in minus T out. P in minus P out. Then what is the inlet temperature? 20. What is the exit temperature? 18. Do not use degrees Celsius. It's going to be 293 Kelvin. This one is going to be 291 Kelvin. You knew that, right? Pretty sure that you knew that. The inlet temperature is, inlet pressure is 240. The exit pressure 200. So this one is 240 kilopascal. Exit pressure is 200 kilopascal. The gas constant is this one, 8.31. 4 divided by 32. What about the specific heat? Let's use the specific heat at 300 Kelvin for convenience. I don't want to do, another linear interpolation. I'm too lazy. Then it's going to be 1.005 kilojoule per kilogram Kelvin. In reality, you need to determine this specific heat at the average temperature. You know that. I know that. I don't want to do that. This is time consuming. Wait, this is air. Don't use this value. This is air. Oh, our system is oxygen. Oh, what am I doing? What am I doing? So I'm going to use this value, 0.918 kilojoule per kilogram Kelvin. So going back, I need to match the arrows. Is that right? This way? No. This is right. So if you do the calculation, we get everything. The rate of entropy generation is going to be 0.1025 kilowatt per Kelvin. Any question about this problem? You want to keep this paper? $10 per paper. The last problem of chapter 6. So after this, we can go to a new chapter, chapter 8, which is very fun. Oh, we want to study chapter 7. So we have a steam expand. So from chapter 1 to chapter 6, they are theory chapters. The chapters for theory parts in thermodynamics, chapter 8 and 9 are going to be the application. So we are going to use what we learned in chapter 3 to 6 to study, some famous thermodynamic cycles such as vapor power cycles or gas power cycles, like how we produce electricity in power plant, or how do we make a car, how this gasoline engine works, how this diesel engine works, how this gas turbine works when you design maybe the big container ship or the jet engine, etc. That's what we are going to study, which is much easier than the theory part of thermodynamics, because you're not going to study anything new. We are going to use what you already know to study the existing the engineering systems in industry. Okay, so we have a steam expands in a turbine. Turbine is an open system. It has inlet and an exit. So we are going to use this energy balance equation. So let me write this energy balance equation here. Q dot over T plus M dot at the inlet. I'm going to say inlet is number 1, exit is number 2. So M dot number 1 S1 minus M dot number 2 S2 plus the rate of entropy generation S dot gen is 0. So that is our governing equation. So the steam expands in a turbine steadily at the rate of 40,000 kilogram per hour. So we have M dot. M dot at the inlet is the same as M dot at the exit, because we only have one inlet, one exit. We have a conservation of mass principle. They're supposed to be the same. So these are 40,000 kilogram per hour entering at 8 megapascal and 500 degrees Celsius and leaving at 40 kilopascal as a saturated vapor. So we have the inlet condition and the exit condition. Can we determine S in, S out, S1, S2? Yes, we can. So at the inlet, we have inlet number 1, we have 8 megapascal, 500 degrees Celsius. What is the phase change process? We all know that, super vapor, but you can make a property diagram to determine that. And at the exit, we have 40 kilopascal saturated vapor. That means phase change process number 4. Oh, we already know the phase change process number 5, number 4. Some people say, I don't know whether it is number 5, so let's verify that. At 8 megapascal, T something diagram, TH maybe, looks like this. The saturation temperature is 8 megapascal, 295. The saturation temperature is 295.1. What is the temperature of our system? Wow, extremely high, 500 up here. So what is the phase change process? 1, 2, 3, 4, and 6. No, 5. So superheat vapor, right? So we have a superheat vapor at the inlet, saturated vapor at the exit. So can you determine S1, S2? Yes, should be very simple. So S1 first. How can we determine S1? You can go to superheat vapor table, supposed to be here. So if you cannot, to pick this up, what can you do? As people studying STEM. The problem is the surface tension. So if you make your surface wet, you can grab that. No? If you go to grocery store, sometimes you need to pick up some cucumber or the lettuce. But sometimes this plastic bag, you cannot open that. So how can you open it? Wet your surface. That will increase the surface tension, so you can open it right away. You don't know that? You remember that, right? When you go to grocery store, there's a vegetables. There are some are wet, so you gently touch and then open the plastic bag. That's engineering, right? Science. Yeah. No, it's a physical phenomenon, surface tension. So when you grab that, the tension between the water between your skin, and so that's a physical phenomenon. If it should be a chemical phenomenon, you need to have a chemical reaction. Water become the hydrogen or oxygen. Since water is remain as water, so you can say it's a physical phenomenon. I don't know why I said that, but we have. I lost. Oh, right, S1. So let's find S1. So we can go to. All right, now remember the surface tension, right? So you can go to the table A4 to determine S1. Where is the S? The last column. So let's find S1. Going smooth. What is the temperature? 500. Oops, not smooth anymore, right? There's no 500. 500 is between 480 and 520. Can you determine specific entropy S? Yes, but you need to do linear interpolation, since you already did many times, right? So I won't do that anymore. So the specific entropy, when you do linear interpolation between these two numbers, then you get 6.723. 6.723 kilojoule per kilogram Kelvin. Okay, that's good. So we know S1. What about S2? Oh, it's a saturated vapor. If you know you have a saturated vapor, how do you determine S2? S2 is the same as S what? F? F is saturated liquid. Sg, saturated vapor at what condition? This condition, 40 kilopascal. So Sg at 40 kilopascal. At 40 kilopascal, Sg, this is the number, 7.67. 7.67 kilojoule per kilogram Kelvin. Then this one goes here. So what about temperature? Assuming the surrounding medium is at 25 degrees Celsius. This is the temperature you are going to use for this T, 25 degrees Celsius. Am I right? No. What is the unit? Kelvin. Yes, right. 298 Kelvin. So we have everything. Can you determine S dot gen? No. What is the problem? Q dot. So what is the solution? There are two solutions. One, assume that it's an adiabatic system. Neglect that. Don't do that. Or second, use another, the equation to determine Q dot. What is that equation? What is the most famous equation in thermodynamics? Energy balance equation. So you can use energy balance equation. What is that energy balance equation? Q dot in, it's going to be long. So let me sit down. Q dot in plus W dot in plus M dot at the inlet number 1. This one has specific enthalpy, kinetic energy, and potential energy is Q dot out plus W dot out plus M dot at the exit number 2. This one has, I don't like this energy balance equation. H2 V2 square over 2 plus gravity times elevation Z2. That's it, right? Now it's a fun time. So we can neglect kinetic energy change and potential energy change. Is there energy transfer by work? Yes or no? No, it's a turbine. Turbine, what turbine does? Yeah, it produces work. So there's a W dot out. Produces work. Does it consume work? No. Let's assume that there is a heat loss because it's going to be hot. Then you can neglect heat addition to a turbine. So we have the rate of enthalpy at the inlet, the rate of enthalpy at the exit. We have a heat loss and energy transfer by work, the turbine work produced. Now, we know M dot. What is that? Here, 40,000. 40000 more zeros. I think that's it. Kilogram per hour. By the way, don't use 40,000 kilojoule per hour. You need to multiply by what? 1 hour is 3,600 seconds, right? Do the unit conversion. 1 hour, 3,600 seconds, right? Don't forget that. And what is the power produced? 8.2. So I'm going to say 8.2. No, 8,200 kilowatt. Always convert all the units to whatever you are familiar with when you the substitute into a governing equation. Do not do a unit conversion here. That is not okay, okay? Then H1, can you find H1? Yes, it is a superheat vapor. So let's go to superheat vapor table. H1 going smooth. I like that. Now there's a H. What is the temperature? 500. Oh, unfortunately, that H1 is not available. So what do you need to do? Another linear interpolation. Not very happy, but you need to do that. And I did it. 3,398. 3,398.05 kilojoule per kilogram. I'm sorry. So we got H1. This one goes in here. What about H2? Can you determine H2? Yes, we know it's a saturated vapor as G. No, Hg at 40 kilopascal. Where is it? Hg at 40 kilopascal. This is the number we are looking for. 2,636.8 kilojoule per kilogram Kelvin. No, there's no Kelvin, my bad. So this one goes here. So we have everything. Can you determine the rate of heat transfer? Now, yes. You can determine the rate of heat transfer. What is it? $258 0.33 kilowatt. And now this one goes, I like this one. Go back to the main equation here. Yeah, I get that, the comments a lot, every semester in the SOS. This guy is drawing too many arrows. But that's all I can do. Talk to the president, give us another screen right here. We have a new president, we need to have a new screen, right? It's thermodynamics. The solution is just too long, that we cannot put everything in the order, unfortunately. So we got this one. So now we have everything. Now let me do one more time. I like that. I kind of get used to it. So the final answer is 11.4 kilowatt per Kelvin. That completes chapter 6. Any question? Huh? Yeah, sure. So the $10, you owe $20. 1 minute later, people are still writing, okay? Any question about chapter 6? So all the hard time is over. Now is a time for rewording. We are going to use whatever we studied to analyze some applications such as vapor power systems. So this is chapter 8, vapor power systems, and chapter 9, gas power systems. What is the difference between vapor power systems and gas power systems? Huh? Yeah, one is vapor and the other one is gas. You're correct. So in this chapter 8, we are going to study the most famous, the power cycles, thermodynamic cycles that use vapor, steam as the working gas. What is that? Power plant. Vapor power plants. When we talk about, the producing electricity, how do we do that? You can come up with, the conventional, traditional fossil fuel power plants. Burn some, the affordable coal or natural gas or anything, to generate high temperature heat and use this heat to produce the working gas, which is the steam. And the steam runs the turbine to produce electricity. That is vapor power plants. You can also think of, another type of power plant such as solar panels that you can install on top of roof and use a different, the process to produce electricity, than this vapor power plant. You can also, come up with, the wind farms. You see a lot, on the road, right? When you take the what is that? 127. It's just 127? M127? M127. So it's M, not US 127? I know it's not I-127, right? I is, the major highways. Well, anyway, if you take 127, you see a lot of wind farms, right? But the main, was right. But the majority of the, the power plants in the United States, we still rely on vapor power plants. Why is that? because it's the most reliable system. When you have a wind farm, sometimes you have a wind constant in this direction. Sometimes, the variable speeds, sometimes changing the direction, so you cannot produce electricity continuously. That is called standalone base load power plant. Base load power plant means that you need to provide electricity, continuously without any interruption. What about solar panel? If you install a solar panel on top of your roof, first, it looks ugly, but that's not a problem. But the problem is that the intermittency of energy supply. So, you cannot produce electricity for 24/7. So, the majority of the electricity we produce, not only in this country, but all over the world, we rely on vapor power plants. So we are going to study vapor power plants. There are, the several different types of vapor power plants, depending on how we produce heat. And we are not going to study, how we produce the heat. We are going to study how do we produce turbine power using that heat. But we would like to know what type of power plants, are there first, right? That's for our common sense. Okay. So there are 4 types of vapor power plants. The first one is, of course, the famous one, fossil-fueled power plant. You burn something, create heat that is going to, produce steam. That steam runs in the power conversion cycle, which is this one. That's simple. The second one is pressurized water reactor. So it's a nuclear power plant. So the main difference between, the fossil-fueled power plant and nuclear power plant is the way we produce heat. In nuclear power plant, we induce nuclear reaction in the reactor that will generate a large amount of heat that is going to produce steam, and the rest of them is the same. We are going to study the rest of them, okay? And the third, the concentrating solar thermal power plant. Did I talk about concentrated solar power? I think I did. In this class or another class? So this is nuclear power plant. So each one is a nuclear reactor. This one is not the turbine, not the reactor. This one is a cooling system. Cooling system, air cooling. So air goes this way and then goes this way. While doing so, it absorbs air from, it absorbs air from the turbine exit. So we can reject waste heat to the outside. Low temperature thermal energy reservoir, high temperature thermal energy reservoir where reactor is. Geothermal power plants. So we make a hole on the ground and pump water on the ground, and we know that the down there is hot, right? Think about volcano. So when steam comes out, we use the steam to run turbine, do all the rest of the things to produce electricity. That is geothermal power plant. So we pump the hot water out of underground, run the turbine, and use the water, from nearby, trying to reject any heat. That's how we produce electricity. The last one is concentrated solar power plant. This is a different type of solar power plant other than the solar panel. So what we do is that we don't have a semiconductors. If you install solar panel on top of a roof, it has a lot of, the semiconductors directly convert the sunlight into electricity. On the other hand, this one, there's no semiconductors. They are all meters, reflect the sunlight into a focal point, this black one on top, trying to increase the temperature up to 1,000 degrees Celsius. We use that heat to produce, the steam and then run the thermodynamic cycle. That's called CSP. Have we talked about that? Yeah. So there are many different ways to produce heat, but what we are going to study is how we can produce work from that heat. So typically, the power plants consist of 4 components. The way how we produce heat. because of this, there are different names. You know, the nuclear power plant, you know, the fossil fuel power plant, you know, the solar thermal power plant, geothermal power plant, etc. Once we, you know, obtain that high temperature heat, we run the boiler to produce steam. The steam goes into the turbine, expands in the turbine to produce turbine work that is going to be connected to a generator to produce electricity, and any waste heat is going to be removed by a condenser which is connected to, let's say, cooling tower or nearby river water or, you know, the lake or ocean to reject any waste heat. Once we reject any waste heat, we use a pump to pump this water back to the boiler to generate steam again, so it can be a cycle. Then what we are going to study is this one. B is called Rankine cycle. So we are going to study Rankine cycle. So this part is how we produce heat. This part is for those, you know, the majoring electric engineering. Part is for cooling system. So this is what we are going to focus on. So this Rankine cycle has 4 components: boiler, turbine, condenser, and pump. So this one is boiler B, this one is turbine T, and this one is condenser C, this one is pump P. So we are going to study how to connect them, how to, you know, study each component thermodynamically and evaluate the performance of the entire cycle. That's what we are going to do. Okay? Sounds very simple. So let's talk about boiler, turbine, condenser, and pump. So we have a boiler, turbine, and condenser, and pump. So they are all connected, right? So we have a pipe, goes this way. Oh, not this way, goes here. So there's a pipe connected between the boiler and turbine. So that's the inlet of turbine. I'm going to say the inlet of turbine is number 1. This state number one is the exit of the boiler and the inlet of the turbine. And we have a condenser, which is the exit of the turbine and the inlet of the condenser. Then we have number 3, which is the exit of the condenser and the inlet of the pump. Then we have number 4, which is the exit of the pump and the inlet of the boiler. So we have 4 states and 4 processes. Then what happens in this boiler? It's going to absorb heat from the surroundings, so there's a Q in. Since you know, the Rankine cycle can run at steady state, so I'm going to say Q dot, the rate of heat transfer into the boiler. This heat is produced by nuclear reaction, or, you know, the concentrating the sunlight, or geothermal power, or, you know, the burning fossil fuel. And because of this heat, we are going to produce steam at high pressure and high temperature. This high pressure, high temperature steam enters this turbine, expands. While doing so, we are going to produce power, W dot T, turbine power. And once the expansion is done, you know, this steam has waste heat, so we are going to remove that waste heat by a cooling system, that is cool condenser. This cooling fluid can be air or the water from nearby river, lake, and etc. Then this steam has no energy, so we are going to provide pumping power W dot P and return back to the boiler so we can make a cycle. This cycle is called Rankine cycle, R. That's the Rankine cycle. And this whole thing can be considered as heat engine. What? So this is a Rankine cycle. The concept is the heat engine. What is the heat engine? Heat engine has two thermal energy reservoirs. One is at high temperature, the other one is at low temperature. The heat transfer direction is from high temperature for the amount of Q dot H. And we reject waste heat to the low temperature thermal energy reservoir for the amount of Q dot L. By doing so, we produce net power. W dot net, in this case, Q dot in is Q dot H, Q dot out is Q dot L. W dot net, which is the net power, is W dot P minus W dot P. What? The engineer mainly does it. Okay. I don't understand your question.
Does the lead engineer when they're on the site, do they do all the manually?
No, it's an automatic system. Automatic system. Otherwise, someone need to, keep, the rotating levers and etc. They watch the conditions at each state, like what is the condition at the turbine inlet, what is the temperature of the steam, what is the pressure of the steam, what is the flow rate of the steam, and they also measure the same at the exit of the turbine, at the inlet of the pump, at the exit of the pump, and make sure that all the values are steady state. If one goes wrong, then you need to stop it or do something to fix it. When you cannot fix it, what's going to happen? The one in Chernobyl, that's what happened. Or the one in Japan, 2013, what happened? The one in Chernobyl, this one failed. And there was a, the explosion. The one in Japan, this one failed. So that because of tsunami, completely ruined the cooling system. So that's when, that we have all the tragic incidents. So we want them to be steady state. In a power plant company, yeah, there's a control tower that that can monitor all the values. In every section, there's a sensors. Or if there's one thing goes wrong, then you need to to find what is the problem with that one. Usually, the way the power plant works, it's not just one system. They have auxiliary systems like a diesel, the engine or something. So if one goes wrong, they run the diesel engine, while we are fixing this one. So that that you can produce electricity, at the same time. Because the worst case is that you cannot produce electricity when there's blackout. That's the worst case, right? But in reality, the way it works is actually it's a very good question, because there are more than the thermodynamic analysis that we can consider. The first one is when you design this kind of power plant system. Let's say that this power plant presently producing 110 megawatt of electric power. let's assume that it is producing 10 megawatts. So it supplies electricity to Mount Pleasant, our campus, Midland, Saginaw, and Lansing. Let's say that this one power plant covers everything. So do you think that is 10 megawatts? Is the average power consumption by the the people or factory in that area? Like, let's say that you are using maybe 1% of the electricity in your house. So there will be about, let's say, 0.1 megawatt of electricity go to your house. Are you using that 0.1 megawatt every, the single time? Not really. Maybe in the summer days, when in summer we consume more electricity than usual at night, or in winter we use more electricity at night for heating than the day, right? Or sometimes, if there is a major sports event, there are more people sitting in their, the living room watching television, spending a lot of electricity, right? So the demand fluctuates. So let's say that, if the demand, I don't know why I'm talking about that, but that's not the subject of thermodynamics, but it's good to know. So let's say the demand, the fluctuate like that. So the peak is going to be 20 megawatt. The lower peak is going to be, let's say, 5 megawatt. The average is going to be 10 megawatt. So if you are, whoever, make the decision for the power grid in state of Michigan. So let's say that you're working for Lansing, the somewhere office, and you need to build a new power plant for this area. Are you going to build either the 20 megawatt power plant, or are you going to build 10 megawatt or 5 megawatt? 10. So let's say this 10 megawatt power plant costs about $1 billion. 20 megawatt costs about $3 billion. 5 megawatt costs maybe $0.5 billion. Which one? So you are going to use this one. So let's assume that you built 10 megawatt power plant. Then, in the daytime when people use more, then there will be blackout. And at night, when the football game is over, then we have electricity. And when there is another game, or when there is one of the chilly days, so we use more heater, then there's a blackout. Does it make sense? You don't want that happens, right? Then you need to find a new job, right? Because whoever the governor is going to replace you. So if you're going to spend $3 billion to make, to build 20 megawatt power plant, you can do so. But the problem is that if you build this one, you are actually losing this much electricity. But somebody needs to pay, for this power plant company. So your electric bill is gonna go to maybe doubled or something. How much do you pay for electricity? For example, I pay about $300 per month. So it goes up to $600 because of that. Do you think that I would be happy about that? No. One thing we can show is that we can guarantee that there is no blackout. So what is the right decision? This one or that one? Of course, you don't want that happen, right? That means one hour in 24 hours per day, we have electricity. Like the third world, right? You don't want that happen. So, which is the right choice between 10 megawatt power plant, which is number one, 20 megawatt power plant number two? How many of you think that number one is the right choice? No one? Number two. Then you're okay increasing your electric utility bill doubled or tripled. Right. So the answer is we built this one. Yeah, you're right. We built this one. Then you may have a question. Okay, if you build the electric, the power plant this way, you can cover this much electricity, So ready is okay. What about this blue? How are we going to take care of this, the high demand? We usually have, this one is called base load power plant. And each, these power plant has auxiliary diesel engine inside. So this one is more expensive. Of course, it has a higher fuel consumption and lower, the thermal efficiency. But we run this one to cover those, the occasional, the peak hours. That's what happened. That is the this is one of the plans from the Department of Energy trying to utilize renewable energy. What is the problem of renewable energy? The intermittency of energy supply. So what about you use that if the electricity is only available on a certain time? Can you match that one to fill this gap? So that is kind of plan. So in the 2050 up to next the tens of years, our plan is that how we can maintain low cost base load power plant, and how can we cover those the occasional peaks by renewable energy sector. So you can combine rather than completely the converting the power plants, conventional power plants to renewable energy, because that's not going to happen in the near days, near future. Okay. Anyway, that is not the subject of this thermodynamics, but good to know, right? Then going back to Rankine cycle. So we have a boiler, turbine, and condenser and pump. Then how can we study each component thermodynamically? In other words, how can we apply energy balance equation for the boiler, for the turbine, for the condenser, and for the pump? That's what we are going to study today. So we have a boiler, we have a turbine, we have a condenser, and we have a pump. For each component, we have one inlet and one exit. The inlet of the turbine is number 1. This is also the exit of the boiler. The exit of the turbine is number 2, which is also the inlet of the condenser. And same goes on, number 3 and number 4. So the first, and we have a heat transfer. This boiler absorbs the heat from outside to that in. This turbine produces power, turbine power, W dot T. This condenser, to reject any waste heat to the surrounding coolant, such as water or air. And this pump observed, the power, that is pumping power to maintain this cycle. That's what happens. Let's study each component thermodynamically. So if you want to study each component, you need to first determine whether it is a closed system or an open system. Always, there are only 2 energy balance equations that you studied. So we assume that they are steady state open system. Can it be transient open system? Yes. We discussed all the tragic accidents already, right? So we want them to be steady state. Then what is the general energy balance equation for steady state open system? By the way, we are going to neglect kinetic energy goes 0 and potential energy change go to 0. Then the energy balance equation is going to be Q dot in plus W dot in as mass at the inlet. This one has enthalpy, and we are neglecting kinetic energy and potential energy, which is going to be Q dot out plus W dot out plus M dot at the exit. This one has enthalpy. That's it. So this is the general energy balance equation, neglecting kinetic energy change or potential energy change. Let's talk about this boiler first. This boiler has Q in, so which is this one. And inlet is number 4. So the inlet is number 4. The exit is number 1. The exit is number 1. So we have 3 terms. So Q dot in plus M dot, by the way, each component has only one inlet, one exit. So M dot number 1, number 2, number 3, number 4, they are all equal. So we can just say M dot. H4 is M dot H1. That is the energy balance equation for this boiler. Okay? Not very difficult, right? Then what is the next? T, turbine. T. In this T, we have inlet number 1. So this one is number 1. Exit is number 2. It produces turbine power. So 1, 2, 3. 1, 2, and 3. M dot H1 is turbine power plus M dot H2. Difficult? Not much. So boiler turbine, BT, and what's next? BTS? No. C. You don't know what it is. I was talking about BTS. No? Oh, yeah. I don't know why I said that. Anyway, so, oh, BTC? Bitcoin? Never mind. So this boiler has Q in. Oh, we are talking about condenser. What am I doing? Condenser has Q out. So this one. Inlet is number 2. Exit is number 3. So this one, this one. So M dot H2 is Q dot out plus M dot H3. Bitcoin and P, price. We have W dot P inlet, this one, P inlet is number 3, exit is number 4. So this one, this one, this one. W dot P is M dot H3 is M dot H4. So these are the 4 energy balance equations. Now, let's move this one to the right-hand side. Let's move this one to the left-hand side. Move this one to the left-hand side. Move this one to the right-hand side. So Q dot in is M dot H1 minus H4. W dot P is M dot H1 minus H2. Q dot out is M dot H2 minus H3. W dot P is M dot H4 minus H3. So these are the 4 energy balance equations for the Rankine cycle. Then, how can you determine the performance of this Rankine cycle? By using thermal efficiency. What is the thermal efficiency? Desired output. What is the desired output? The net power that we developed, right? What is the required input? The amount of heat transfer that we provide. So W dot net is going to be W dot T minus W dot P, because we produce this turbine power, but some of the turbine power is going to be used as a pumping power. So the net power is going to be our turbine power minus the pumping power divided by Q dot in, then how can we calculate that? W dot T is this one, W dot P is this one, Q dot in is this one. So H1 minus H2, M dot minus M dot H4 minus H3 divided by M dot H1 minus H4. You can cross M dot M dot M dot out. So that's how you evaluate the performance of this Rankine cycle. The last one is called back work ratio. That means how much power, out of the one that you produces is actually going back to the Rankine cycle to run the pump, because the turbine power, not the 100% of the turbine power can be converted to electricity, because some of this turbine power is going to be used to run this pump, right? So I want to know how much, the pumping power out of turbine power, that is the back work ratio. That is H4 minus H3 over turbine power, H1 minus H2. And the value is usually very small, 1 to 2%, which is pretty good. So the Rankine cycle has a pretty good efficiency because the back work ratio is pretty low. What is the counterpart of this Rankine cycle? The Rankine cycle uses, the water as the working gas. Then, can we use this, the steam power plant to run any other thermodynamic cycle? Can you use a steam power cycle to run your car engine? No, you can't. What about jet engine? Can we use a steam power plant in one of the wings on your airplane? Not necessarily. Then what is the working gas for those systems? Can be air, can be carbon dioxide, can be sodium, can be any other materials other than water. In that case, this back work ratio goes up to 40 to 60%, which will drop the efficiency dramatically. And why do we use those, the gas power cycles? Because it has its own advantage. What is the major disadvantage of this steam power cycle? Yeah, it's just too big. So can you install steam power, the plant for your car? No. For airplane? No. So the size is one of the major problems. But the thermal efficiency is extremely high, pretty good, because it has been studied over last 200 years. So the technology is very high. So we get extremely high, the thermal efficiency, greater than any other, the technology we have developed practically. Laboratory scale, we have, the other technologies, but they need more time to be used as a commercial sector.
So do you think that's
For this one? For the others, yes. For the others, yes. But presently, this one has the best, the highest efficiency, practically. Then, what is another disadvantage other than the size? What is the material that we use for this one? Water. What is the limitation of water? Then let's think about what is the limitation of nuclear power plant, and what is the working fluid for a nuclear power plant? We use a steam, right? Then is it ideal to use a steam? No. Then what is the limitation of water? Have you heard about heavy water nuclear reactor? Light water nuclear reactor. What is light water? The water in your water bottle, that's a light water. What is heavy water? It's a water, but has more neutron than the typical water. Can you drink? No, you can't. But it behaves like a water, but it has higher maximum temperature. So if you use heavy water in a nuclear power plant, you can increase the temperature of the turbine inlet. Temperature goes up. So it will give you higher efficiency. Can you go to higher efficiency than that? Yes, if you have a fluid that can go beyond the maximum temperature. So the problem of the limitation of this vapor power plant is that at a certain temperature, above this temperature, water cannot, exist anymore. That is called supercritical system. So if you consider only thermodynamic cycle, the higher the efficiency, the higher the temperature, you get the higher the efficiency. If you remember, thermodynamic efficiency, which Carnot efficiency is 1 minus TL over TH. You remember that. To increase this value, what you can do? Decrease the temperature of the coolant. We don't want that to happen, right? Climate change. So the only way you can do is that increase the temperature of the source. How can you increase the temperature of the source? When we have, then it's very simple. You just need to replace water with another material that has higher, the maximum temperature. That's why we say, the carbon dioxide as working gas because it has a higher maximum temperatures. Liquid sodium, helium, there are high pressure helium. There are many, many different materials are proposed. So to use them, we cannot use Rankine cycle. So we have to rely on gas turbine that we are going to study in the next chapter. But the limitation of the gas turbine system is that the backwork ratio is way higher. So this one, backwork ratio is only 1 or 2%. So if you produce 10 megawatts, only 1% is going to be used to run the cycle. But if you use a gas turbine, if you produce 10 megawatts, about 5 or 6 megawatts, more than half, goes back to the cycle, which is bad. So each system has pros and cons. So you need to do an economic decision to decide which one is better than the other for a particular application. Anyway, that's it for today. I finished it 3 minutes.